Hello there. Today you join me and my colleague as we go over Chapter 5, which is all about pressure. First, let us define pressure. Pressure is the force exerted by gases and liquids due to their weight, such as the pressure of the atmosphere on the surface of the Earth and the pressure containerized liquids exert on the bottoms and the walls of a container they are in. Pressure units are measure of force acting over a specified area. It is most commonly expressed in pounds per square inch or in pascals in metric units. Now, there are two ways to look at pressure. One, on the small scale action of individual air molecules, or two, the large scale action of large number of molecules. On the small scale, from the kinetic theory of gases, a gas is composed of a large number of molecules that are very small relative to the distance between molecules. The molecules of a gas are in constant random motion and frequently collide with each other and with the walls of any container. During collisions with the walls, there is a change in the velocity and therefore a change in the momentum of the molecules. The change in momentum produces a force on the walls. This is directly related to the gas pressure. Pressure of a gas is the measure of the average linear momentum of the moving molecules of a gas. On the large scale, the pressure of a gas is a state variable, like the temperature and density. The change in pressure during any process is governed by the laws of thermodynamics. Here is a table for the specific weights and specific gravities of some common materials, including water, glycerin, mercury, and acetone. We'll be discussing the meaning of specific weights and specific gravities in the next slide. First, we have density, or defined by ρ, is defined as the mass per unit volume of a material, or pound per cubic foot, kilogram per cubic meter. Density can refer to the number of molecules in a substance. This can apply to gases, liquids, and solids alike. Specific weight or gamma is defined as the weight per unit volume of a material. It's a pound per cubic foot or Newton per cubic meter. Specific weight can also be defined as the product between density and gravitational acceleration. Specific weight, unlike density, is not absolute and depends on the value of gravitational acceleration, which varies depending on altitude and latitude. Specific gravity of a liquid or solid is a dimensionless value, since it's the ratio of two measurements in the same unit. This is defined as the density of a material divided by the density of water, or it can be defined as the specific weight of the material divided by the specific weight of water at a specified temperature. The specific weights and specific gravities of some of the common materials are in the table that I have just presented. The ease with which specific gravity can be precisely determined leads to its widespread use in chemical science and technology. For example, determination of specific gravity is a part of routine characterization of a new liquid compound. Specific gravity of most organic compounds containing only carbon, hydrogen, and oxygen is less than 1. Among the devices used to measure specific gravity are the Westphal balance, pincometer, and hydrometer. Now we have static pressure, dynamic pressure, and impact pressure. Static pressure is the pressure of fluids or gases that are stationary or not in motion. Point A is considered as static pressure, although the fluid above it is flowing. When the fluid is stationary or the fluid near walls of flowing pipe has static pressure, the fluid molecules near the walls of the pipe have zero velocity. The reason for this is the surface of the pipe, which has zero velocity, holds back the molecules of fluid that are near the walls due to friction between them. This phenomenon is called the boundary layer. Dynamic pressure, on the other hand, is the pressure exerted by a fluid or gas when it impacts on a surface or an object due to its motion or flow. Impact pressure, or the total pressure, is the sum of the static and dynamic pressures on the surface of an object. Here we have figure 5.1, an illustration of the static, dynamic, and impact pressures. Point A is considered a static pressure, although the fluid above is flowing. In this figure, the dynamic pressure is B to A. In point B depicts the impact pressure. Now we have pressure measurement. There are 6 terms applied to pressure measurements. They are as follows. The total vacuum which is zero pressure or the complete lack of pressure, which would be what we experience if we were in outer space. The vacuum is a pressure measurement made between total vacuum and normal atmospheric pressure, which is 14.7 psi. A vacuum can be created by removing air from space using a vacuum pump or by reducing the pressure using a fast flow fluid, as in Bernoulli's principle. Atmospheric pressure is the pressure of the Earth's surface due to the weight of the gases in the Earth's atmosphere or the air, and is normally expressed at sea level at 14.7 psi or 101 kilopascals. However, this is dependent on several atmospheric conditions. The pressure decreases above sea level and at an elevation of 5,000 feet drops to about 12 psi. Now we have absolute pressure. This is the pressure measured with respect to a vacuum and is expressed in pounds per square inch, absolute or PSIA. Measurements taken in absolute pressure use this absolute zero as the reference point. The best example of an absolute reference pressure is a measurement of barometric pressure. In order to produce an absolute pressure sensor, the manufacturer will seal a high vacuum behind the sensing diaphragm. Therefore, if you hold open the process pressure, absolute pressure, the air would be absolute barometric pressure. Gauge pressure, on the other hand, is the pressure measured with respect to atmospheric pressure and is normally expressed in pounds per square inch gauge, PSIG. Gauge pressure is measured in relation to ambient atmospheric pressure. Changes of atmospheric pressure due to weather conditions or altitude directly influence the output of gauge pressure. Sensors at gauge pressure higher than ambient pressure is referred to as positive pressure. If the measured pressure is below atmospheric pressure, it is called negative or vacuum gauge pressure. Gauge pressure sensors usually only have one pressure port. The ambient air pressure is directed through a vent hole or a vent tube to the back of the sensing element. Vented gauge pressure transmitter allows outside air pressure to be exposed to the negative side of the pressure sensing diaphragm so that it is always measured with reference to the ambient barometric pressure. Therefore, a vented gauge pressure sensor reads zero pressure when the process pressure connection is held open to the atmospheric air. Differential pressure is the pressure measured with respect to another pressure and is expressed as a difference between two values. This will represent 2 points in the pressure of the system and is referred to as delta P. All pressure readings are considered differential pressure readings as pressure is measured as absolute pressure in relation to a vacuum, or in the case of gauge pressure, in relation to atmospheric pressure. Here we have a table for pressure conversions from with relating to water and when relating to mercury. You have an illustration of A, the gauge pressure, at figure A, and here we have at figure B, delta or differential pressure. Here we have a number of measurement units that are used for pressure. We have pounds per square foot or PSF, or most commonly as pounds per square inch. We also have atmospheres and pascals or Newton per meter squared or kilopascals. We have torr, which is 1 millimeter of mercury, and bar, which is 1.013 atmospheres or 100 kilopascals. Then we have pressure points. This is the pressure that is exerted by a fluid at equilibrium at a given point within the fluid due to the center force of gravity. Hydrostatic pressure increases in proportion to depth measured from the surface. Because of the increasing weight of fluid exerting downward force from above. If fluid is within a container, then the depth of an object placed in that fluid can be measured. The deeper the object is placed in the fluid, the more pressure it experiences. This is because the weight of the fluid is above it. The more dense the fluid above it, then the more pressure is exerted on the submerged object due to the weight of the fluid. The pressure is given by P is equal to gamma times H, where P is the pressure in pounds per unit area or pascals. Gamma is the specific weight, which is pound per cubic feet in English, or newtons per cubic meter in SI units. H is the distance from the surface in compatible units. Head. Head is sometimes used as a measure of pressure. It's the pressure in terms of a column of a particular fluid. Or 1 head of 1 foot of water is the pressure that would be exerted by a 1 foot tall column of water. That is 62.4 pounds per square feet gauge. But the pressure exerted by 1 foot of head of glycerin would be 78.6 pounds per square foot gauge. Now, the hydrostatic paradox states that the pressure at a given depth in a liquid is independent of the shape of the container or the volume of the liquid contained. The pressure value is a result of depth and density. The total pressure of forces on the sides of the container depend on its shape, but at a specified depth. Now we have buoyancy. Buoyancy is the tendency of an object to float in a liquid. All liquids and gases in the presence of gravity exert an upward force known as the buoyant force on any object immersed in them. Buoyancy results from differences in pressure acting on opposite sides of an object immersed in a static fluid. The buoyant force is the upward force exerted on an object wholly or partly immersed in a fluid. This upward force is also called upthrust. Due to the buoyant force, a body submerged partially or fully in fluid loses its weight, appears to lose weight rather, or it appears to be lighter because the buoyant force. Now, the buoyant force is given by B times gamma times V, where B is the buoyant force in pounds Gamma is the specific weight. V is the volume of the liquid displaced. If working in this figure, point A, B, and C and D are all of the same size. The buoyancy forces on A and C are the same, although their depth is different. There is no buoyancy force on D, as the liquid cannot get under it to produce the force. The buoyancy force on B is half of that on A and C, as only half the subject of the object is submerged. Now we move on to Pascal's law. According to Pascal, now we know that pressure is equal to the force divided by area on which it acts. Pascal's principle, also called Pascal's law, states that in a fluid, gas or liquid mechanics, at rest in a closed container, a pressure change in one part is transmitted without loss to every portion of the fluid and to the walls of the container. The principle was first enunciated by the French scientist Blaise Pascal. According to Pascal's principle, in a hydraulic system, a pressure exerted on a piston produces an equal increase in pressure on another piston in the system. If the second piston has an area 10 times that of the first, the force on the second piston is 10 times greater, though the pressure is the same as that on the first piston. This effect is exemplified by the hydraulic press based on Pascal's principle, which is used in such applications as hydraulic brakes. Pascal also discovered that the pressure at a point in a fluid at rest is the same in all directions. The pressure would be the same on all planes passing through a specific point. This fact is also known as Pascal's principle. Since the pressure is transmitted through the liquid to the second cylinder, the force on the larger piston, Fl in this case, is given by F of L is equal to pressure times A of L, where A of L is the cross-sectional area of the large piston. Assuming that the pistons are at the same level, from which F of L is equal to A of L times F of S all over A of S. Here in the figure, can be seen that F of L is magnified by the ratio of the piston areas. This principle is extensively used in hoist, hydraulic equipment, and the like. Okay, now we move on to the vacuum. A vacuum is very difficult to achieve in practice. Vacuum pumps can only approach a true vacuum. Good small volume vacuums, such as a barometer, can be achieved. Pressures less than atmospheric pressure are often referred to as negative gauge and are indicated by an amount below atmospheric pressure. For example, 5 psi gauge would correspond to 9.7 psi atmosphere, assuming that atmosphere is 14.7 psi. Now we move on to the measuring instruments for pressure. A manometer, by definition, is a device used for measuring the pressure of a fluid by balancing it against a predetermined column of fluid. The most common type of manometer, which almost all us might have seen, is a sphygmomanometer used to measure blood. It is the device which doctors use to measure our blood pressure. A manometer can be used at any applicative process where the pressure of fluid needs to be measured. Of course, we have different types of manometers. We have first up, U-tube manometers. This type of manometer is, well, as the name suggests, U-shaped, with one end open to the atmosphere. It is used for measuring suction. has the capability of measuring both positive and negative suction pressures. It utilizes the pressure of a specific gravities for measuring the suction pressure. This type of manometer generally has a liquid whose specific gravity is greater than that of the fluid whose suction pressure is to be measured. When there are equal pressures on both sides, the liquid levels will correspond to the 0 point. The scale graduated in pressure units. When a pressure is applied to one side of the U-tube that is higher than the other side, the liquid rises. The liquid rises in the lowered pressure side, so that the difference in the heights of the two columns of liquid compensates for the difference in pressure. The pressure difference is given by P sub r minus P sub L is equal to gamma times the difference in height of the column liquid in the columns, where gamma is the specific weight of the liquid in the manometer. Now we have inclined manometers. This is a high precision and high accuracy type of manometer used to measure the minuscule amount of pressures with the highest of accuracy. Its configuration is inclined, as the name suggests, and this makes it more accurate than most types of manometers. It's used where manometric properties of liquids are very close. Of course, we also have well manometers, which are alternatives to inclined manometers for measuring low pressures using low density liquids. In the well manometer, one leg has a much larger diameter than the other leg, as shown in this figure. When there is no pressure difference, the liquid levels will be the same height for a zero reading. An increase in the pressure in the larger leg will cause a larger change in the height of the liquid in the smaller leg. The pressure across the larger area of the well must be balanced by the same volume of liquid rising in the smaller leg. The effect is similar to the balance of pressure and volume in hydraulic jacks.
So diaphragms, capsules, and bellows. So gauges muna tayo. Gauges are a major group of pressure sensors that measure pressure with respect to atmospheric pressure or pressure na normally nating nafe-felt. So gauge sensors are usually devices that change their shape when pressure is applied. These devices include diaphragms, capsules, bellows, and Bourdon tubes. So diaphragms muna tayo. Consists of a thin layer or film, usually a flexible material, supported on a rigid frame and will be shown later in the figure. Pressure can be applied to one side of the film for gauge sensing, or pressures can be applied to both sides of the film for differential or absolute pressure sensing. A wide range of materials can be used for the film, such as rubber or plastic for low pressure, silicone for medium, stainless steel for high pressure. When pressure is applied to the diaphragm, the film distorts or becomes slightly spherical. These movements can be sensed using a strain gauge, piezoelectric, or changes in the capacitance technique. So strain gauge, ito yung nagko-convert ng force or pressure into electrical resistance. Piezoelectric, ito naman yung electrical charge na nag-accumulate sa solid material na ma-release lang through mechanical stress. So, the deformation in the above sensing devices uses transducers to give electrical signals. So, transducer, ito yung parang device na convert ng one signal to another form of signal. So, dito, ito yung parang pressure to electrical signal. Of all these devices, the micro machine silicon diaphragm is the most commonly used industrial sensors for the generation of electrical signals. So, silicon diaphragms uses silicon, which is a semiconductor. This allows a strain gauge and amplifier to be integrated into the top surface of the silicon structure after the diaphragm was etched from the back side. This device has built-in temperature compensated piezoelectric strain gauge and amplifiers that give a high output voltage. They are very small and accurate, 2% FSD or full-scale detection, reliable, have a good temperature operating range, are low cost and can withstand high overloads, have good longevity, and are affected by many chemicals. Commercially made devices are available for gauge, differential, and absolute pressure sensing up to 200 psi. This range can be extended by the use of stainless steel diaphragms to 100,000 psi. So figure 5.7a shows the cross sections of the three configuration of the silicon chips used in micro miniature pressure sensors, i.e. gauge, absolute, and differential. The given dimensions illustrate that the sensing elements are very small. The die is packaged into a plastic case. The die, by the way, is an integrated circuit. A gauge assembly will be shown later in B. The sensor is used in blood pressure monitors and many industrial applications and is extremely used in automotive pressure sensing applications such as manifold air pressure, barometric air pressure, oil, transmission fluid, brake fluid, power steering, tire pressure, and the like. So makikita natin dito na ito yung configuration for the gauge. So ito yung diaphragm, ito siyang part na to. Tapos ito yung parang exposed port para sa atmospheric pressure. So pag nagkaroon ng additional pressure, so mag-stretch siya, magiging semi-spherical siya dito. Pag absolute naman, vacuum dito para may vacuum reference siya. So pwede lang siya mahigop hanggang dito. Pwede lang siya ma-push hanggang dito. Tapos meron naman tayong differential or pwede natin apply to both sides para malaman kung yung difference ng dalawang pressure. So meron naman tayo dito na miniature gauge sensor. Ito yung parang whole package na siya. So merong silicon die dito, merong electrical leads na present ng signal, this is yung pressure port. Parang yung obvious part na nakalabas na pwede mong saksak sa mga bulbs na bibigay ng pressure. So capsules are two diaphragms joined back to back. Pressures can be applied to the space between the diaphragm, forcing them apart to measure gauge pressure. So pwede siya mag-expand doon ay yung expansion na yun yung sinusukat sa capsule type na sensoring device. The expansion of the diaphragm can be mechanically coupled to an indicating device. The deflection in a capsule depends on its diaphragm, material thickness, and elasticity. Materials used are phosphor, bronze, stainless steel, and iron nickel alloys. The pressure range of instruments using these materials is up to 50 psi. Capsules can be joined together to increase the sensitivity and mechanical movement. So yung diaphragm para siyang isang thin material lang, no? Sa capsule parang pinag-join siya together back to back. So pwede mong mag-insert ka ng pressure dito, may expansion niya, yun yung measure. So yung bellows, ito mamaya yan. So ito na nga, bellows are similar to capsules except that the diaphragms instead of being joined directly together are separated by corrugated tube or tube with convolutions. When pressure is applied to the bellows, it elongates by stretching the convolutions and not the end diaphragm. So alam niyo yung instrument na accordion. So similar lang dito yan. The materials used for the bellows type of pressure sensor are similar to those for the capsule, giving a pressure range for the bellows of up to 800 psi. Bellows devices can be used for absolute differential pressure measurement. So ito nga yung bellows, para siyang layer siya ng capsules na pinagpatong-patong. So differential measurements can be made by connecting two bellows mechanically, opposing each other when pressure is applied to them. We'll be shown later the figure. When pressures P1 and P2 are applied to the bellows, a differential scale reading is obtained. So ito nga yung differential bellows pressure. So may dalawa tayong bellows. Pressure 1, pressure 2. So let's say mas malakas yung pressure 1, syempre mag-elongate to. Tapos kung mas mahina naman, mag-shrink. So yung difference ng dalawang pressure na to, sila yung magtitip ng scale. So magbabago ng analog input dito sa scale natin. So figure 5.9b shows bellows configured as a differential pressure transducer driving a linear variable differential transformer to obtain electrical signal. P2 could be the atmospheric pressure for gauge measurement. So may included naman tayong transducer dito from one signal to another. So, from pressure to electrical signal. So, ito yung no? So, pag nag-input to ng pressure dito, itong transducer na to, siya mag-input ng electrical signal dito. Tapos yung meron tayong pressure to magagarap na lang siya bilang gauge pressure na siya para sa atmospheric pressure. The bellows is the most sensitive of the mechanical devices for low pressure measurement. So, Bourdon tubes naman tayo. Bourdon tubes are hollow cross-sectional beryllium, copper, or steel tubes shaped into a three-quarter circle. They may be rectangular or oval in cross-section, but the operating principle is that the outer edge of the cross-section has a larger surface than the inner portion. When pressure is applied, the outer edge has proportionally larger total force applied because of its larger surface area, and the diameter of the circle increases. The walls of the tubes are between 0.01 and 0.05 inches thick. The tubes are anchored at one end so that when pressure is applied to the tube, it tries to straighten, and in doing so, the free end of the tube moves. So basically, pag nag-apply ka ng pressure dito sa side na ito, yung Bourdon tube, try niya straighten sarili niya at magkakos ng movement sa other end. So, maapektuhan niya ito, mapupush niya ito, at ang after effect nun, yung indicator ay gagalaw from here to right side. Mas malakas yung pressure, syempre, mas mag-stretch yung Bourdon tube. So, ito nga yun. Movement, magtitip siya ng scale. This movement can be mechanically coupled to a pointer which, when calibrated, will indicate the pressure as a line of sight indicator, or it can be coupled to a potentiometer to give a resistance value proportional to the pressure for electrical signals. Figure 5.10b shows a helical pressure tube. This configuration is more sensitive than the circular Bourdon tube. The Bourdon tube dates from the 1840s. It is reliable, inexpensive, and one of the most common general-purpose pressure gauges. So, ito yung helical Bourdon tube. Bourdon tubes can withstand loads up to 30 to 40% of their maximum rated load without damage, but if overloaded, may require recalibration. The tubes can also be shaped into helical or spiral shapes to increase their range. The Bourdon tube is normally used for measuring positive gauge pressure, but can also be used to measure negative gauge pressures. If the pressure on the Bourdon tube is lowered, then the diameter of the tube reduces. This movement can be coupled to a pointer to make a vacuum gauge. So, Bourdon tubes can have a pressure range of up to 100,000 psi. Figure 5.11 shows the Bourdon tube type of pressure gauge. When used for measuring negative pressure or vacuum, it is the A, and for positive pressure, it is the B. Note that the A is counterclockwise movement and B is clockwise movement. So, other pressure sensors. So, meron tayong barometers. Barometers are used for measuring atmospheric pressure. A simple barometer is the mercury barometer shown below. It is now rarely used due to its fragility and the toxicity of mercury. The aneroid barometer is favored for direct reading, and the solid-state absolute pressure sensor for electrical outputs. A piezoelectric pressure gauge is shown in figure above. Ito yan. Piezoelectric crystal, pag nagkaroon ng stress yan, mag-release siya electrical charge. A piezoelectric pressure gauge is shown above. Piezoelectric crystals produce a voltage between their opposite faces when a force or pressure is applied to the crystal. This voltage can be applied in the device used as a pressure sensor. Capacitive devices use the change in capacitance between the sensing diaphragm and a fixed plate to measure pressure. Some micro-machined silicon pressure sensors use this technique in preference to a strain gauge. This technique is also used in a number of the other devices to accurately measure any small changes in diaphragm deformation. So, vacuum instruments naman tayo. So vacuum instruments are used to measure pressures less than atmospheric pressure. The Bourdon tube, diaphragms, and bellows can be used as vacuum gauge but measure negative pressure with respect to atmospheric pressure. So yung mga na-mention natin dating sensors, pwede siya maging vacuum gauge kaso negative yung output. The silicon absolute pressure gauge has a built-in low pressure reference, so it is calibrated to measure absolute pressure. Conventional devices can be used down to 20 torr. The range can be extended down to about 1 torr with special sensing devices. Application consideration. When installing sensors, care should be taken to select the correct pressure sensor for the application. So ano ba yung mga dapat natin consider? So first, selection. Pressure sensing devices are chosen by the pressure range, overload requirements, accuracy, temperature, operating range, line of sight reading, or electrical signals, and response time. In some applications, there are other special requirements. Parameters such as hysteresis and stability should be obtained from the manufacturer's specification. Hysteresis, parang ito yung value ng physical property na naglalag behind. For most industrial applications reading positive pressures, the Bourdon tube is a good choice for direct visual readings and the silicon pressure sensor for the generation of electrical signals. Both types of devices are commercially available sensors to measure from a few PSI FST up to 10,000 PSI. So ito pa yung mga table na take in consideration mo. So yung difference nila. Difference between Bourdon sa silicon sensor. Ito pa yung approximate pressure ranges for pressure sensing devices. Ito yung maximum range nila. So installation. The following should be taken into consideration when installing pressure sensing devices. 1. Distance between sensor and source should be kept to a minimum. Sensors should be connected via valves for ease of replacement. Overrange protection devices should be included at the sensor. To eliminate errors due to trapped gas in sensing liquid pressures, the sensor should be located below the source. To eliminate errors due to trapped liquid in sensing gas pressures, the sensor should be located above the source. When measuring pressures in corrosive fluids and gases, an inert medium is necessary between the sensor and the source, or the sensor must be corrosion resistant. The weight of the liquid in the connection line of a liquid pressure sensing device located above or below the source will cause errors in the zero, and a correction must be made by the zero adjustment, or otherwise compensated for in measurement systems. Resistance and capacitance can be added to electron circuits to reduce pressure fluctuation and unstable readings. So calibration. Pressure sensing devices are calibrated at the factory. In cases where a sensor is suspect and needs to be recalibrated, the sensor can be returned to the factory for recalibration, or it can be compared to a known reference. Low pressure devices can be calibrated against a liquid manometer. High pressure devices can be calibrated with a dead weight tester. In a dead weight tester, the pressure to the device under test is created by weights on a piston. High pressures can be accurately reproduced. So summary. Pressure measurement standards in both English and SI units were discussed in this section. Pressure formulas and the types of instruments and sensors used in pressure measurements were given. So main points of discussion, definition of the terms and standard use in pressure measurements, both gauge and absolute pressures. English and SI pressure measurement units and the relation between the two, as well as atmospheric, torr, and millibar standards. Pressure laws and formulas used in hydrostatic pressure measurements and buoyancy together with examples. The various types of instruments including manometers, diaphragms, and micromachine pressure sensors, various configurations for use in absolute and differential pressure sensing in both liquid and gas pressure measurements. In the application section, the characteristics of pressure sensors were compared, and the consideration that should be made when installing pressure sensors were given. So thank you for your attention. God bless.